AI and machine learning is complicated. Often we'll find online tutorials and guides that will take us to the foundational levels of machine learning. And very often that boilerplate takes a lot of time to learn because AI can be rather complex. However, there's a very common pattern that works in the majority of cases when you're trying to do basic artificial intelligence using the most foundational approach to machine learning. You can even do it in a Google spreadsheet. So I built here a Google spreadsheet that walks us through how machine learning works, and you'll be able to see it with your hands-on using a Google spreadsheet. There's no plugins and no external tools. It's just the spreadsheet itself. Let's get started with the introduction tab here that we have. We've got multiple tabs just to let you know. We've got some examples that we're gonna walk through, but first we're gonna start off. We need to know our purpose. That is the hardest problem with AI and machine learning, is we need to know what is the ultimate goal. You have to start with that. Usually it's a question or a desired outcome, and then you're able to tune and target for that outcome, and then the AI will take care of defining all the rules for you automatically. So using just a basic approach, we need our starter question: will the Y Combinator startup be successful? That's a very good question. That's a very straightforward question, and machine learning can help us get that answer. In order to get our artificial intelligence up and running, we have to start with a couple of things. We need to know what our target is, and we need the data for the AI to be able to learn from. So we got started by having an example question of our outcome. We are looking for, will the Y Combinator startup be successful? And then we've got here some example data from the past where we have startups A through B, D, C, and D with some features. We've got some features that we've assigned to these startups that we think are going to be relevant. And even what you want to do is go further than this and provide a lot more features. We can add in like quarterly growth rate, location, incorporation, even the name of the company, the go-to-market strategy, available channels that you can use to target prospects. There's so many options. So we picked 3 just to get started here. It says, are they using AWS, Amazon Web Services? Is their team size greater than 3? Like they have more than 3 people on the team. And do they have a greater than 50% revenue growth over a period of time? It could be like maybe in this case a year. And then we have all of our historical records for these past startups. Then what we get to do is take that data, put it into a model, and then allow a computer to derive hyperplanes within a deep neural network to make generalized predictions of future startup outcomes. So if we wanted to do things like algorithmic trading, we could do it using this approach. This is a supervised training technique. Usually you can Google support vector machine and you'll be able to sort of see a common machine learning approach that is going to be represented here in this spreadsheet as we walk through it. Matrix multiplication is the foundation for all machine learning and artificial intelligence. Every algorithm, even the modern most advanced ones, use matrix multiplication as the foundation for how the core of the AI model works. What we're going to do is, using a Google spreadsheet, is we're going to zoom in on that. And the next step here is, now that we've got our question, which is a desired outcome, will the Y Combinator startup be successful? And then we have our input data, which is the features. Using AWS, the team size greater than 3 and 50% revenue growth. The next step is vectorization. So the AI, in order to do matrix multiplications, has to be done in numerical values. So we'll take human concepts like using AWS as a feature flag and convert that into number notation. This is what we call vectorization. In our case, we're keeping it simple. For the features, they're going to be a yes or a no on the features, and then we're going to vectorize them into a 1 or a 0. Now the data is ready to fit into our model. For simplicity, I've excluded one specific column, which is the output data that's necessary when training. For example, here we would have the answers for historical data. So we have our startup A, B, C, and D. We already have the historical records for those startups. We would already have their outcome of success. So now we've vectorized our data and we're ready to go to the next step. Now we're getting into the magic of artificial intelligence and AI. In the background, there's a thing called a matrix. And this matrix is just a set of numbers, often referred to in the industry as the parameters, the number of parameters. They're also referred to as the weights. These are the model weights that are used during the matrix multiplication process. They're also the coefficients. They're all the same. There's so many words for this. So in our spreadsheet here, we're looking at step 3, and we have ourselves a set of weights in 2 different matrices. And this is as basic as we can get, essentially. You can get a little bit more basic by reducing the resolution of the weights, but to relay the concept, I've made it at this size right here, which is fairly simple. The initial weights are always typically randomized. So we've started it off using indy array, which generates a random array initially. Now you could start with all ones or all zeros, but if you do that, you're gonna have to change your input strategy, and it's easier just to start with random. And you do the same for the output layer as well. So we've got two separate matrices here. And this is it. This is the brain. That's the intelligence is right there. That's the core of the knowledge learned. Yes, right now they're just random numbers, but the idea is with machine learning is that we're going to feed in data and then capture an output and then see how far off the AI was. Did it get the answer right? If it didn't, we're gonna go back propagation and we're gonna change these values ever so slightly, incrementally, a little bit at a time. And then this is the machine learning process, the training part. And after a number of iterations and enough data, you'll have a generally purposed trained AI that will be able to give you fairly high accuracy on your original question. Will the Y Combinator startup be successful? So now that we've defined our initial brain of the AI, we can actually use it as the next step. We're gonna feed in the data and see how correct the answer is. That's the next thing that we got to do. So now let's try it out. We have our AI that we use to generate with a random number. This is an untrained AI at this point, and we want to see how good it is at finding our answer. And I expect that it won't be good at all. So here we're looking at the screen, we see that we've got our AI hidden weights, the parameters, or the coefficients, what you can call them, all sorts of fun things. We're gonna take our input data, which are the labels that we vectorized, and then we're gonna multiply those into this matrix, and then we're gonna get some outputs here. Here in the top corner of our function, we see the formula. So in Google Spreadsheets, we have an array formula that's able to multiply two matrices. And we have our input data and our weights, our parameters, the model parameters. Now, just this one step alone is that core foundation that are embedded in every AI model today. Even the really big fancy ones like those large language models. They all do this, matrix multiplication. Now we go a step further and we add an activation function. Now this isn't strictly required. However, in terms of making sure that our output data, as it goes in between layers, sort of stays within a bounds of reason, we want to make sure to keep a sort of a gradient of understanding. Otherwise, it's really easy for numbers to explode to infinity. There's other approaches that you can use that prevent that or avoid it altogether. However, for a general purpose, it's always good to have an activation function. There's more than one activation function you can use: tan, sigmoid, ReLU, and leaky ReLU. The ReLUs are they're faster, they're easier to calculate, and they're a little more popular these days. They do require a little more parameters and things like that to get better results. My favorite is tan H. I like tan H because it provides us a wide range of gradients, including a -1 to +1. Whereas a sigmoid is usually 1 to 0. We get an extra bump of more space below into a -1. And it also is good for maybe binary scenarios. Although you could say 1 is true and 0 is false in a sigmoid, I still tend to find tan H gives me a little bit better results. The challenge with tan H is that and sigmoid is that they are more computationally expensive, but they're great for general purpose and for smaller model weights, which is what we have here. We have very few weights and very few parameters here. So once we've multiplied our vectorized input data into our hidden layer, that gives us a result output with these values here. This is temporary data that we're going to be using to pipe into the next layer, which is going to be our output layer. And our output layer is going to be very simple in this case, where we're just going to do a matrix multiplication of our output layer weights, which is part of our original model, to the hidden results that we received from our initial layer, which is going to give us the output of these values here. And that's the answer. These are the output answers. This is what the output for. In all scenarios, you're always going to get a numerical answer as the output. And now the AI has done its job. It basically has done everything that we needed it to do. We haven't trained it yet, so it's not very good at giving us good answers, but it did give us answers. In this case, it gave us these numbers here, which are kind of meaningless. You can go a step further by assigning meaning to those values, which is you need to decide how you want to interpret them. And then based on your interpretation, you can go back and train the model and force it to learn new things. So say since our question is, will the Y Combinator startup be successful? We'll want to train this model to target the success of the numbers that we know of these startups. Startup A, B, C, and D, they're historical startups, so we know if they're successful or not. And what we'll do is compare the output from the model with the truth of the history, and then go back and then modify these weights and these weights, the entire model, just ever so slightly, a little bit at a time based on the data. And then eventually we will get our answer, and the AI will be smart and give us good outcomes. Let's train our AI model. We have a Google Spreadsheet set up that is going to be training an AI model using only Google Spreadsheet. No plugins and nothing fancy. It's all embedded in the Google Spreadsheet using spreadsheet formulas. My favorite hello world for machine learning in general is an Exor. The Exor operator when comparing two Boolean values. Just like an OR operator or an AND operator. It's kind of funny to say in a row. The Exor operator will have a target output based on the input. With the Exor operator, if you're not familiar, the two input values will be true or false, and if they're both true or both false, the result will be false. That's the Exor value. If they're different from each other, one value is true and the other value is false, or the other way around, then the Exor is going to return true. And that's what we're going to train an AI to do. We're going to train it to learn how to use this kind of operator, how to determine the result. So we have all of our truth. We have all of our training data right here. This is 100% of our training data. So this is why I really like this example, because it's a game where we know fully the picture of every possibility. So we have our initial model weights, which are going to be randomized floating point numbers. And we're going to do a feed-forward neural network, which is the industry standard for all modern AI. We're going to take our input data and we're going to feed it through the network. And we're going to take the output of the AI and we're going to use that information based on how accurate it is to then go back and correct ever so slightly the model, these weights, these coefficients, the model parameters. So we're going to go to step 4 here, which is our feed forward. We're going to take that data, the input data, and then we're going to pass it forward, multiplying it into our model. And then we get our output results here. Now, what we're going to do is take these outputs results, which is what the AI thinks is the answer. We know it's wrong because it's going to be wrong initially, unless we get really lucky. We can actually, that is possible. You can create a randomly generated AI that does a pretty good job, or it might do a really good job. But that is very rare, and it's probably not the best way to do AI machine learning. Although you could. In this case, we're going to use a gradient descent approach. We're going to take the output results here. We're going to determine the error, like how far off it is from the actual answer that it needs to be, right? This says the output answer is 2.29, but it's actually supposed to be 0. And so this is the error amount. This is how far off that value is. And so what we need to do is on a learning rate of 10%, correct towards 0. We take the error output and multiply it by our learning rate, and that gives us our gradient layer that we are going to be using to back propagate and slightly modify our matrix. So when we were doing feed forward before, we have to go backwards. So we'll modify our output layer first, and then we'll modify the hidden layer. As we're going backwards, we also need to unwind the tangent function as well with arctangent. Transpose our matrix, which means we just rotate it. Then do matrix multiplication, which will sprawl it out into our gradient. This is the correction values that we need to apply to our original model. And then this gives us the new model weights for the new hidden weights. We did it! We did it! One step through, one time. So what we want to do is do that several times over and over and over until we get to our desired outcome. So that way the model will always know what the answer is based on its input. There is one trick that I employed here that I didn't mention at the beginning, was the bias layer, that I added in an extra digit here. This is a trick that allows us to make sure that as we're training our model, none of the values in the hidden layer or output layer get locked. It's possible for certain paths in this model to become nulled out and become unusable, specifically because there are some paths where the data that's being inputted into the matrix is going to be multiplying by 0. And this is a problem. This will lock out some of those neurons or those hidden parameters. And so in order to take advantage of the most amount of data and keeping our gradient pretty smooth, we want to make sure that we have a bias layer. There's other ways to go about this as well. In this case, I just set the bias layer to 1, so that way it allows us to proceed forward with our desired outcome. Usually, a bias layer in deep learning will be included in the model as an extra matrix that's associated with every single layer in the matrix. But in this case, I just kept it simple. And I like this. This is a neat little trick, and it works really well. And we're going to see how that works here in the following tabs. This is something I really wanted when I was learning about AI. I wanted to be able to see what was going on behind the scenes in the picture. What does it look like underneath? And it looks like a spreadsheet with a bunch of floating point numbers. So can Google Spreadsheets actually be used to create a machine learning scenario? And yes, the answer is yes. We can do it. It can be done in Google Spreadsheets, and it is here. I have a spreadsheet that has done it for us, and it uses only Google Spreadsheet math. So we're going to use Google Spreadsheets to be able to train a model that will accurately, basically 100% of the time, be able to run an operator. In this case, it's the Exor operator. Here's my input data and the output results of that data. When the values match on either side of the operator, the output result will be false. In this case, it's 0. So if we got true, true, the answer is false. False, false, the answer is also false. But if they're different, then the output of Exor operator is going to be true. So we want to train an AI to be able to accurately provide this output just based on this data alone. This is all the information it has, and we're going to train it. And this spreadsheet does that. And we can see every single step of the way as you scroll down. These are the number of training cycles that we put it through. So we always have the same input training data. And as we're moving forward, we need to take the output from the previous learning, apply it to our model that we have, our input model, and provide an output every single time on the prediction. So we can see here's the output. It's the prediction. It's what the model thinks is the answer. And when we're starting here at the top, it's always kind of in the middle in our case because we started with a 0.5 bias. So the fun part is as we scroll down here in the spreadsheet, we can see how the training starts affecting the predictions because the predictions have this target output. While this row here or this column here is the target, the output, the AI says, this is the data, this is the value that I think it is. We're going to interpret that value by seeing at what side of 50% is it on, right? Is it above 0.5 or is it below 0.5? And we're going to use that to train the AI, and as we're making targets, we convert that data by rounding the output into a 0 or a 1. And then we're using that as our determined output to train the model. And as you can see pretty quickly, it immediately gets to 100% correct and 100% accurate. At the beginning, it wasn't so good, right? It was getting some pretty poor numbers randomly, but just after a few steps, it didn't take long, and now it's very, very accurate. And we can see that visualized here through each cycle, each training set. The blue bars here are represented as accuracy and how accurate it is. Basically, we want 100% in this case because it's a known quantity of the input data and our desired output. So we always want 100% in this case. When we're training for more general purposes and the values aren't always Boolean or they might need to be interpreted in other ways, we're going to want a wider gradient. So we'll use a different training approach. But for this approach, it works perfectly fine. You can also see the error bar here. The error bar is going to tell you how far off it is from the actual answer that we're desiring. If we're saying the output prediction value is 0.47, but it needs to be 0, then we're going to say how far that we need to adjust it for. If our training, based on our training, or our learning rate, it's called a learning rate. So if we scroll all the way to the bottom, we can see what our model weights look like differently, trained and untrained. Here at the top, we've got the untrained initialized random values. You can see that right here on the initial rows. And at the very bottom here, this is the fully trained model weight. This is what it looks like when it's smart, when it has the answers. And if you're looking at it, they kind of look pretty close to the same. It's kind of hard to discern what's going on there. But this is where the magic of AI comes in. It's able to create these pattern detections and identify hyperplanes that will perfectly allow it to align to our target input and outputs. And then going forward, we can just ask the question of the AI, what is the answer to this? And it will give us a very highly accurate answer. Oh, it's really good. Specifically, if we also have boundaries assigned to it, we're always going to get 100% accuracy and correctness. And that's the power of AI. Using Google Spreadsheets, we machine trained our own artificial intelligence. Now, it's a very simple one, but in this case, it's a good demonstration of how this works. The first approach that we use used in the Google spreadsheet was standard gradient descent. However, we can go one step further. Once we have a larger volume of data, we need to do something that allows a better capturing of the sample data and generalization in the model. The challenge is when we are using this approach with just standard gradient descent, it's very possible that we'll have overfitting. With overfitting, it means that the AI is always going to tend towards very specific answers, and it won't be able to generalize across various other answers that could be accurate. So there's another common approach to be able to deal with this by using something called stochastic gradient descent. And the results look a little bit different because things jump around a lot more. During the training process, essentially the idea with stochastic gradient descent is there's randomization. We take the training input data set, and with every batch that we input into the model, we randomize that batch. Say you have a very large volume of data, many examples. You need to be able to put all that data into the AI so it knows to understand that that's one of the things to learn. It needs to learn. But if you do it in a fashion where it's just linear, then it's very likely that you'll be in a scenario where you overfit, and it will have a general tendency towards a direction that you might not want. It will give you less quality answers. So in order to prevent that, you can use something like stochastic gradient descent, just randomizing the data set. And it looks like this. Just like before, we start with our randomized matrix initializations. The difference this time is, though, as you can see here, when we input our training data, it's different every single epoch. One epoch is running through the training set completely end to end for all of your possible training data points. That's one epoch. A batch is taking a subset of that data, putting it through the model until the number of times that you put it into the model to train it, you will then achieve one epoch at that point, once you've covered every single data point. And so with our stochastic approach here, we're always randomizing the data as it goes in. So you can see it's different every time. The shape is different. For a simplicity perspective, we're always taking that entire data set and we're feeding it through the model because we have a fully known value end to end. What we could do is we could batch it, like say do half of them and then input that in and then randomize again, do another half, and just keep going from there. That's another approach. You could do that as well. That helps with generalization. If we have a full picture of our data, we don't need to do that. We can just do everything in batches and it's gonna be more efficient. So if we take a look at the beginning near the early stages of training, that the predictions of the model output are fairly blankish. They're not fully trained yet. We see that the values are not exactly equal to where they should be. They're getting close. They're approaching there, right? This 0.45 is closer to 0 and 0.76 is closer to 1. When we look at the final value here, we see that they're a lot closer to what they need to be. The ultimate result of this spreadsheet was able to create essentially 100% accuracy on the desired question here. In our case, our question was an operator, the Exor operator, which takes two input values and compares them and has a desired output to match the standard Exor operator. And it works! It's success! Now, if you want to go even further, you can continue the number of epochs and iterate until these numbers are essentially perfect. And you can get there, you can do it, you can get these numbers to essentially go all the way to the desired targets. They're just ever so slightly off, but if you keep going, you'll be able to get there. And check it out. Here's the gold. Here's the magic. The parameters, right? You hear about these LLMs and the parameters and like a billion parameters. Well, those compute that requires in the GPUs and the lots of money and energy to produce those, it's right here. These values. Those derived values are what drives the AI. This is the exciting part. This is where, right, that's where all the gold is essentially, right? You want those numbers. That's the target. These are the parameters, the model weights, the coefficients of the model. This is just something that I really wanted to see when I was getting started with machine learning. I really wanted to see visually the step-by-step process in a simplified approach that's typically universally understood. I'll make sure to include this Google spreadsheet in the comments so that way you can see and scroll through it yourself to watch every single epoch as the model trains and learns. You can even play with the hyperparameters, right? The learning rate here, you can change that to something like smaller, for example, and then it will render in front of you and you can see the values. You can see as we have a smaller learning rate, it takes it a little bit longer to train. But if you put the learning rate too high, it'll explode. All right, let's put it really high. Let's see what the 60%, see what happens. Yeah, that's a problem. You don't want to see that. So you'll typically want to put it at a fairly moderate learning rate. And usually even in which the challenge is in the bigger models, you need to make that learning rate even smaller. So as you add more and more parameters and larger amounts of data input values, as you're training through stochastic gradient descent, you'll need to make sure that those hyperparameters are adjusted and tuned for your specific use case.